Environmental Science article. Environmental Biosafety and Risk Assessment. Biosafety refers to the principles, practices, and measures implemented to ensure the safe handling, containment, and control of biological materials in order to prevent accidental exposure or release of potentially harmful agents. This field is essential in various settings,
including
laboratories, healthcare facilities, and biotechnology industries, where work involves the manipulation of living organisms or biological
materials.
The main objectives of biosafety are to protect individuals, communities, and the environment from the potential risks associated with the handling of biological agents. These agents can include bacteria, viruses, fungi, toxins, and other microorganisms that may pose a threat to human health, animal health, or the environment. Biosafety measures are typically classified into different levels based on the degree of risk associated with the biological materials being handled. The classification ranges from Biosafety Level 1, BSL-1, which involves basic safety practices for handling low-risk agents, to Biosafety Level 4, BSL-4, which requires the highest level of containment and is reserved for handling dangerous and exotic agents posing a high risk of transmission and severe illness. Key components of biosafety include the use of personal protective equipment, proper laboratory design and facilities, rigorous containment
procedures,
and thorough training of personnel. Adhering to biosafety guidelines and regulations helps ensure that scientific research and applications involving biological materials are conducted in a responsible and secure manner. History of biosafety. The historical development of biosafety can be traced back to the mid-20th century, with significant advancements occurring in response to the increased understanding of microbiology and the potential risks associated with handling biological materials. Here are some key milestones in the historical background of biosafety. 1. Post-World War II period, 1940s, 1950s, the end of World War II saw increased interest and research in microbiology, virology, and other biological sciences. The development of vaccines and antibiotics, as well as the emergence of genetic engineering, raised
awareness about
the need for safety measures in laboratories. 2. Asilomar Conference, 1975. The Asilomar Conference on Recombinant DNA marked a pivotal moment in the history of biosafety. Scientists gathered to discuss the potential risks associated with genetic engineering and recombinant DNA technology. As a result,
conference
guidelines were established to ensure the safe handling and containment of genetically modified organisms. 3. Emergence of biosafety levels, BSLs, in the 1980s. The Centers for Disease Control and Prevention, CDC, in the United States developed a system of biosafety levels, BSLs, to categorize
laboratories
based on the level of containment required for handling different biological agents. This system helped standardize safety practices and facility design. 4. Ebola virus outbreak, 1976, and other emerging diseases. Outbreaks of highly infectious diseases, such as Ebola, highlighted the need for strict biosafety measures. These events prompted increased international attention
and collaboration
to address the containment of dangerous pathogens. 5. Global Biosafety Framework. In the 1990s and early 2000s, international organizations such as the World Health Organization, WHO, and the World Organization for Animal Health, OIE, played a crucial role in developing global biosafety guidelines. These guidelines aimed to establish common principles and standards for biosafety practices worldwide. 6. Bioterrorism concerns. The early 21st century
heightened
the awareness of the potential for biological agents to be used for malicious purposes. This concern led to increased focus on biosafety and biosecurity measures to prevent accidental releases and deliberate misuse of biological materials. 7. Advancements in
biotechnology.
As biotechnological advancements continued, with developments like synthetic biology and gene editing, biosafety measures evolved to address the challenges posed by these emerging technologies. Today, biosafety continues to be a dynamic field, adapting to new scientific discoveries and
technological
innovations. International collaboration and the establishment of comprehensive guidelines and regulations contribute to maintaining a high level of safety in laboratories and other facilities working with biological materials. Objectives of biosafety. The objectives of biosafety guidelines are to establish a framework of principles, practices, and measures that ensure the safe handling, containment, and control of biological materials. These guidelines aim to protect individuals, communities, and the environment from potential risks associated with working with biological agents. The specific objectives of biosafety guidelines include 1. Protection of personnel. Ensure the health and safety of individuals working with biological accidental exposure or infection. This materials by minimizing the risk of includes providing and promoting the use of personal protective equipment, PPE, and implementing safe hazards associated with specific work practices. 2. Prevention of laboratory-acquired infections. Minimize the risk of laboratory-acquired infections among personnel by implementing appropriate containment measures, training programs, and adherence to biosafety practices. This includes practices such as proper hand hygiene, safe handling techniques, and the use of containment equipment. 3. Environmental protection. Prevent the release of biological agents into the environment by implementing containment measures and waste management practices. This includes proper disposal of biological waste, decontamination procedures, and measures to prevent accidental spills or leaks. 4. Community safety. Protect surrounding communities from potential hazards associated with the handling of biological materials. This involves ensuring that laboratories and facilities are designed and operated in a manner that minimizes the risk of transmission of infectious agents to the external environment. 5. Compliance with
regulations.
Ensure compliance with national and international
regulations
and guidelines related to biosafety. This includes adherence to specific biosafety levels, BSLs, and other standards that are established to categorize laboratories based on the risk associated with the
biological
agents being handled. Biological agents and laboratory procedures. Develop and implement risk management strategies to mitigate identified risks. 9. Emergency preparedness. Develop and implement plans for responding to emergencies, accidents, or incidents involving biological materials. This includes having procedures in place for containment breaches, spills, and other unforeseen events. 10. Continuous improvement. Promote a culture of continuous improvement in biosafety practices. Regularly review and update guidelines, procedures, and training programs in response to new scientific knowledge, technological advancements, and changes in the nature of biological work. By achieving these objectives, Biosafety guidelines contribute to the responsible and ethical conduct of research, healthcare, and industrial activities involving biological materials, ultimately protecting the well-being of individuals and the broader community. Biorisk assessment is a systematic process used to identify, analyze, and evaluate the potential risks associated with the working of biological agents in various settings, such as laboratories, healthcare facilities, and research institutions. The primary goal of biorisk assessment is to ensure the safety of personnel, the community, and the environment by identifying and implementing appropriate control measures to manage and mitigate the identified risks. Here are the key steps involved in biorisk assessment. 6. Facility design and
Maintenance.
establish and maintain facilities that are designed to meet the appropriate biosafety level requirements. This involves
Consideration.
such as controlled access, proper ventilation, and physical containment features to prevent the accidental release of biological agents. 7. Training and education. Provide comprehensive training and education programs for personnel working with biological materials. This includes training on safe
Laboratory practice.
emergency response procedures and awareness of
Potential hazards.
8. Risk assessment.
And management conduct.
Risk assessments to identify and evaluate potential. 1. Identification of biological agents. List and categorize the
Biological.
agents that will be used or manipulated. Consider the characteristics of each agent, such as its
Pathogenicity.
virulence and mode of transmission. 2. Determination of activity and scale. Define the nature and scale of the activities involving
Biological.
agents. Assess factors like the volume of materials, the frequency of manipulations, and the methods of handling. 3. Assessment of potential hazards. Identify and analyze potential hazards associated with each biological agent and the
Activities.
involving them. Consider the route of exposure, potential for aerosolization, and any additional risks specific to the agents. 4. Evaluation of personal exposure. Assess the potential for
Personal exposure.
to biological agents during the various stages of the work. Consider factors such as handling techniques, use of personal protective equipment, PPE, and the effectiveness of containment measures. 5. Identification of control measures. Propose and evaluate control measures to mitigate identified risks. These may include
Engineering.
controls, administrative controls, and the use of PPE. Consider the implementation of biosafety cabinets, vaccination programs, containment equipment, and other preventive measures. 6. Emergency response planning. Develop plans for responding to accidents, spills, or incidents involving biological materials. Establish procedures for containment breaches, personal exposure, and the safety
Evacuation.
of the facility if necessary. 7. Review of facility design and infrastructure. Evaluate the design and infrastructure of the facility to ensure they meet the biosafety level (BSL) requirements for the activities being conducted. Consider factors such as ventilation, access controls, and waste management. 8. Training and education. Assess the competence of
Personnel and provide
appropriate training on safe work practices, emergency response procedures, and the use of protective equipment. Ensure that personnel are aware of the potential hazards and control measures associated with their work. 9. Documentation and record keeping. Document the biorisk assessment process, including the identified hazards, control measures, and emergency response plans. Maintain records of personnel training, facility inspections, and any incidents or near misses. 10. Periodic review update. And regularly review and update the biorisk assessment in response to changes in activities, personnel, or scientific knowledge. Consider new information about the biological agents being handled and the effectiveness of control measures. And biorisk assessments are crucial for maintaining a safe working environment, preventing accidents or exposures that could lead to the release of hazardous biological agents. These assessments contribute to the overall biosafety management of facilities handling biological materials. Assessment of risk during laboratory research. Assessing the risk during
Laboratories research involves systematically evaluating
the potential hazards associated with the research activities and implementing measures to minimize or control those risks. Here are key steps and considerations in assessing and managing risk during laboratory research. Times 1. Identify hazards. List and characterize
the biological
agents, chemicals, equipment, and processes involved in the research. Identify potential hazards associated with each component, such as toxicity, flammability, or biological risks. PD July 2024/99. 2. Assess hazards. The severity of evaluate the severity of the identified hazards, considering factors like toxicity levels,
infectiousness,
and potential for harm. Prioritize hazards based on their potential impact on personnel, the environment, and research outcomes. 3. Evaluate exposure routes. Identify potential routes of exposure for laboratory
personnel exposure,
including inhalation, ingestion, skin and injection. Contact. Consider how the research activities may generate aerosols, spills or other potential exposure pathways. 4. Determine exposure. Likelihood of. Assess the likelihood of exposure to hazards during various research tasks and activities. Consider factors such as frequency of handling, volume or concentration of materials, and effectiveness of containment measures. 5. Assign risk levels. Categorize the overall risk associated with each hazard by combining the severity and likelihood assessments. Use a risk matrix or other tools to determine risk levels and prioritize areas that require attention. 6. Implement control measures. Develop and implement control measures to mitigate
or eliminate
identified risks. This may include engineering controls, administrative controls, and the use of personal protective equipment (PP). Examples of control measures include fume hoods, biosafety cabinets, vaccination programs, and training on safe laboratory practices. 7. Emergency response planning. Develop and communicate emergency response plans for potential incidents, spills, or exposures. Ensure that laboratory
personnel are
trained on emergency procedures, including
evacuation,
containment breaches, and first aid. 8. Facility design and engineering controls. Evaluate the design and infrastructure of the laboratory to ensure it meets safety standards and biosafety level (BSL) requirements. Implement engineering controls such as ventilation systems, eye wash stations, and emergency showers to enhance safety. 9. Training and education. Provide comprehensive training to laboratory personnel on the specific hazards associated with their work. Ensure that researchers are aware of the proper use of equipment, handling techniques, and emergency response
procedures.
10. Regular monitoring and auditing. Point. Establish a system for regular monitoring and auditing of laboratory practices, equipment, and safety protocols. Conduct safety inspections and assessments to identify areas for improvement and ongoing compliance. 11. Documentation and record keeping. Maintain detailed records of risk assessments, control measures, training, and incidents. Document any changes in
procedures,
equipment or personnel that may impact safety. 12. Continuous improvement. Review and regularly review and update risk assessments in response to changes in research activities, personnel, or scientific knowledge. Encourage a culture of continuous improvement in laboratory safety practices. By following these steps and integrating a comprehensive risk management approach, laboratories can create a safer working environment and minimize the potential for accidents, exposures, and adverse events during research activities.